Hi everyone, welcome to this lesson. Have you ever noticed that when S1 is fighting a battle, you can easily control its gimbal to move agilely to aim your opponents. In addition, gimbal offers very stable images when you are using first-person view in the app. So in today's lesson, we are going to learn what is gimbal. Then we're going to learn the motion of gimbal on S1. And in the end, we're going to do some programming on the project Target Practice. In the Target Practice project, we place 3 visual markers in front of the S1 robot. S1 can aim at visual markers with numbers from small to large, record their positions, and then hit them in sequence. First, we need to store the data of the yaw and pitch axis of the gimbal using a list, and then extract data from the list and assign them to the 2 axes of the gimbal, so as to allow the gimbal to quickly rotate to the specified position. First of all, we need to know what is a gimbal. In reality, a gimbal is a portable device that is mounted on camera to allow people to manually adjust the angle of the camera as needed. With greater requirements for image stability, gimbals are evolving in the context of film and television production. There are currently 3 primary types of gimbal in general use. They are fixed gimbals, motorized gimbals, and stabilizing gimbals. A fixed gimbal is typically used to capture still objects. When we mount a camera onto the fixed gimbal, we can manually adjust the angle of the camera as needed. Therefore, a fixed gimbal is typically used as a tripod to support the camera. A motorized gimbal is a fixed gimbal that is equipped with a motor. It allows the user to control the angle of the gimbal by controlling the rotation of the motor. This type of gimbal is typically mounted onto a surveillance camera. Motorized gimbals require a lot of effort and resources to set up and normally will not be moved after being mounted. A stabilizing gimbal is a type of motorized gimbal built by adding attitude control to a fixed gimbal. Attitude control allows the gimbal to maintain stable, even when carrying an object. A gimbal motor is mounted around the camera of a drone to help maintain the camera stability even when the drone flies fast. This is the gimbal of S1. It is a stabilizing gimbal with 2 motors mounted onto the bottom and the side of the blaster. The motor on the bottom of blaster, known as yaw axis motor, allows the gimbal to move left and right. The motor on the right side of the blaster, known as pitch axis motor, allows gimbal to move up and down. To control the gimbal of S1, we need to control the pitch angle and yaw angle respectively. Well, I guess it is the first time you hear the words pitch angle and yaw angle, so what are they? To define these angles, the first thing we're going to do is to set up a fixed local tangent plane coordinate system. So here it is. In this coordinate system, the x-axis points to north. The y-axis points to east. And the positive z-axis points to the center of the Earth. And this coordinate system is also called NED system, which represents north, east, and down. This coordinate system is fixed and will not move with the gimbal of S1. So besides this NED coordinate system, we also need to set up a chassis coordinate system, which moves with the chassis. So if this is the chassis of S1, the origin of its coordinate system is at the geometric center of chassis. And the x-axis points to the front of chassis and y-axis points to the right. The z-axis is actually perpendicular to the plane that formed by x and y, which is in this direction. Lastly, we also need to set up a gimbal coordinate system. So if this is the chassis, and this time we have a blaster on it, and muzzle is pointing to that direction. Okay, so the origin of this coordinate system is actually at the intersection of yaw axis and pitch axis, which is over here. And the x-axis is actually pointing to the direction of Muzo. And the y-axis is in 90 degrees to the x-axis. And similar to this case, the z-axis is actually perpendicular to the plane that's formed by the x and y-axis, which is in this direction. So at this stage, let's do a very quick summary. So now we have 3 coordinate systems, and this is called local tangent plane coordinate system, or NED coordinate system. And the one in the middle is called chassis coordinate system. And the one on the right is called gimbal coordinate system. With these 3 coordinate systems, we can accurately define the yaw angle and the pitch angle. When the gimbal rotates 45 degrees around the z-axis of the gimbal coordinate systems, the x-axis of the gimbal coordinate system, and the axis of the local tangent plane coordinate systems, these 2 coordinate systems will form an angle of 45 degrees, which is the yaw angle of the gimbal. When the gimbal rotates 30 degrees around the y-axis of the gimbal coordinate system, the z-axis of the gimbal coordinate system and the z-axis of the local tangent plane coordinate system will form an angle of 30 degrees, which is the pitch angle of the gimbal. This allows us to clearly describe the gimbal coordinate system. The purpose of the gimbal control technology is to control the axis motors. The motor controls are divided into speed control and position control. Speed control involves allowing a motor to quickly attain desired speed, and position control involves allowing a motor to quickly reach the specified position and stay still. Let's take a position loop as an example. The purpose of controlling the position of gimbal is to stabilize the gimbal so that it will be held in the desired position if and when disturbance occurs, such as when we manually rotate the gimbal. For example, if we write the following program and run it on the S1 robot, we'll find that the yaw axis of the gimbal will finally return to the preset position no matter how we move it. To hold the gimbal in a certain position, we need to use a sensor that measures angle, which is called a linear Hall sensor, to read the actual angle of the gimbal. After obtaining the data of angle, the intelligent controller can use the control technology to rotate the gimbal to the specified position. In reality, we typically use a PID controller to eliminate the difference between desired position and the position obtained from the sensor. You can learn more about PID control in the Accurate Object Tracking video. So here is the block diagram of the control system applied on the gimbal control of S1. We put desired position as an input to the system, and the system will complete the closed loop by using the feedback signal provided by the sensor, which allows S1 to adjust the gimbal to the specified position. Here we use PI controller. The actuator here is the DC motor driver, and the object being controlled is the DC motor inside the gimbal. Now we are up to the programming part. In this part, we'll program S1 to realize target practice project. This process involves 3 steps: identify the target, create a rating function, and record the data about the gimbal. We need to enable visual marker identification. Next, use the module for identifying and aiming at number 1, which allows the gimbal to be accurately held in the position of the number 1. At this point, we only need to add the attitude angle of the pitch axis of the gimbal and the attitude angle of the yaw axis of the gimbal to the end of the created list. Repeat this action for the other 2 visual markers. Secondly, read the data in the list and identify and shoot at the targets. Now that we have stored the orientation and position of the gimbal for the visual markers 1, 2, and 3. Next, we need to aim and shoot at the targets. Send the gimbal angles stored in the list to the yaw and pitch axis of the gimbal respectively, and launch a gel bead, thus reading the first data. By adding 2 to the variable I, we can obtain the attitudes of pitch and yaw axis for the number 2. Thirdly, add the shoot function to the maintain thread, thus completing the design of the entire program. Run the program to hit the target visual markers. Great, so we've done the programming part as well. Now let's do a recap for today's lesson. In the first place, we learn what is gimbal. We know that there are 3 types of gimbal, and they are fixed gimbal, motorized gimbal, and stabilizing gimbal, which is used on our S1. Secondly, we learned something about the motion of gimbal by introducing 3 different coordinate systems and the PID control technology applied on the gimbal control. And in the end, we did some programming to realize a project called Target Practice. So this is all for today's lesson. I will see you next time.